You know what cold feels like. You've felt it, the ache in your hands, the burn in your lungs on a freezing morning. You have never felt anything close to space. The coldest place on Earth is a research station in Antarctica, minus 89 degrees. Deep space is minus 270. Not 3 times colder. The gap is so wide that our record-breaking, humanly unsurvivable Antarctic winter is about 68 times warmer than the empty space above your head right now. 3 degrees. That's all that separates deep space from absolute zero, the point where every atom stops moving and there is no colder to go. That's the number. And by the end of tonight, you'll know what it does to a human body, where the coldest place in the universe actually is, and why the number is the least terrifying thing about it. Now get yourself comfortable, hit subscribe, we begin. 2.72548 Kelvin, that is the number. That is the temperature of deep space. And before we do anything with it, we should sit with it for a moment, because almost everyone has heard something close to this figure, and almost no one has ever been told what it actually means. Kelvin is a temperature scale, like Celsius or Fahrenheit. The difference is where it begins. Celsius starts at the freezing point of water. Fahrenheit starts at a reference point chosen by a man in the 1700s. Kelvin starts at the coldest temperature the laws of physics permit anything to be. 0 on that scale is not a convenience. 0 on that scale is the floor of reality. So when we say 2.72548 Kelvin, we are saying something very specific. We are saying less than 3 degrees above the bottom of everything. In the units you grew up with, that is minus 270.42 degrees Celsius, minus 454.76 degrees Fahrenheit. Look at those decimal places for a second, because they are doing more work than you might think. This value comes from a 1999-era instrument called FIRUS, flown on NASA's COBE satellite, and refined in a 2009 review by the physicist Dale Fixon, who pulled together every reliable measurement in the scientific literature. The uncertainty on that number is 57 thousandths of a single degree. Think about what that level of precision means. Imagine measuring a running track 100 meters, about 328 feet, and knowing its length to within 2 centimeters, less than an inch. That is how well we know the temperature of the emptiest places we can point an instrument at. We know the coldness of the universe better than most of us know our own height. Absolute zero sits at minus 273.15 degrees Celsius, minus 459.67 Fahrenheit. Here is what happens there, in plain terms. Everything you have ever touched is trembling. The atoms in this table, in your skin, in the air in front of your face, are vibrating constantly, and that vibration is not caused by heat. That vibration is heat. Temperature is nothing more than a measure of how violently the small things are moving. Absolute zero is the point where that restless jostling would finally stop, where matter would go completely, perfectly still, and we can never get there. Not because our equipment is not good enough, because the universe forbids it. In 1912, the German chemist Walter Nernst formulated what we now call the third law of thermodynamics, and its most accepted version says something remarkable. No process, no matter how idealized, can bring a system to absolute zero in a finite number of steps. Picture emptying a room of air with a pump that can only ever remove half of what remains. One stroke, half gone. Another stroke, half of the remainder. You can keep going forever and get astonishingly close to empty, but you will never take the last molecule out. Cooling works the same way. The closer you get to zero, the harder every further step becomes, and the final step never arrives. The floor of the universe exists. Nothing is permitted to stand on it. So let's put 2.7 Kelvin where it belongs on that scale, right at the very bottom, almost touching a place nothing can reach. To see how far down that is, we need something familiar. Liquid nitrogen is the coldest substance most people will ever see with their own eyes. The stuff that flash freezes a flower until it shatters like glass. It boils at 77 Kelvin, roughly minus 196 Celsius, minus 320 Fahrenheit. Measured up from the absolute floor, that is 28 times higher than the temperature of deep space. Go colder. Liquid helium is what keeps the superconducting magnets in an MRI scanner working, the coldest fluid humans handle in any routine way. It boils at 4.2 Kelvin. Deep space is colder than liquid helium. Think about that for a moment. The most extreme cryogenic liquid in a modern hospital, the one that requires specialist handling and elaborate insulation just to exist, is warmer than the ordinary background of the cosmos. Now bring it home to the coldest thing that has ever happened on this planet. At 2:45 in the morning on July 21st, 1983, at the Soviet research station at Vostok, high on the East Antarctic Plateau, a thermometer registered minus 89.2 degrees Celsius, minus 128.6 Fahrenheit. The World Meteorological Organization still recognizes it as the lowest air temperature ever directly measured at Earth's surface. More than 40 years later, nothing has beaten it. That is a cold so severe that exhaled breath freezes into visible fog before it clears your face, and ordinary steel becomes brittle enough to fracture. On the absolute scale, that record reads 184 Kelvin, which means the worst cold this planet has ever produced. The single most hostile temperature in the history of human measurement sits roughly 68 times further from absolute zero than the empty space between the stars. Our record is the universe's resting state. Our extreme is its ordinary. And now we have to take all of that away from you. Because that number, the one we just spent all this care establishing, precise to 5 decimal places, verified across dozens of independent measurements, does not tell you what space would feel like, not even approximately, if you stepped out of an airlock expecting minus 270 degrees to hit you the way an Antarctic wind hits you. You would be wrong about almost everything that was about to happen to your body. The question contains a hidden trap, and to see it, we have to correct something almost everyone believes about cold itself. Cold is not a substance. You cannot bottle it, ship it, pour it, or step into it. No container of cold exists anywhere in the universe, because cold is not something that arrives. Cold is a description of something leaving. Picture a single candle burning in a large, unheated room in winter. We say the room is cold, and the flame is warm, but nothing is flowing from the room into the flame. Only one thing is moving: energy, leaking outward from the fire into everything around it, in one direction, always. The chill you feel standing in that room is not an arrival. It is a departure, yours. Every sensation of cold you have ever had in your life has been that. Your own heat going somewhere else, which explains why winter air is so brutally effective. Air feels like nothing. It is not nothing. When you stand outside on a freezing night, the molecules of that air are striking every square centimeter of your exposed skin, billions upon billions of times every second. Each impact is a tiny transaction, a fragment of your body heat handed over permanently to a molecule that immediately bounces away and is replaced by another. Your nerves do not report the temperature of that air. They cannot. What they report is the rate at which you are losing yourself into it. And this is the part that sounds wrong until you have felt it. Your body has no ability to sense temperature at all. What it senses is heat flow. You already have the evidence, and you have had it your whole life. Wherever you are sitting right now, there is probably something metal within reach, a doorknob, a chair frame, the edge of a laptop, and something wooden or fabric nearby. Both have been sitting in the same room for hours. Both are at exactly the same temperature. Touch them one after the other and the metal feels distinctly, unmistakably colder. It is not colder. not by a fraction of a degree. Metal simply conducts heat away from your skin far faster than wood does. Your hand drains into it more quickly, your thermoreceptors fire harder, and your brain, which has no direct access to temperature, reports the only thing it can measure: speed of loss. The metal is not cold, the metal is fast. Hold on to that, because it is the key to the whole thing. Now ask the original question again, carefully. How cold is space? The question quietly assumes that space is a material, a medium you could immerse yourself in, the way you immerse yourself in air or water, something that could press against you and pull your warmth away. But vacuum is not cold stuff. Vacuum is the near total absence of stuff. Let's be precise about how absent. Take a single cubic centimetre of the air in this room, a volume about the size of a sugar cube. Inside it, at sea level, sit roughly 25 billion molecules. If you tried to count them one per second, you would need something close to 800 billion years. That is more than 50 times longer than the universe has existed. Now take that same sugar cube volume out into interstellar space, between the stars. On average, you would find one atom. One. And that is the crowded part. In the space between galaxies, the average density drops to something like a single atom per cubic meter, a volume the size of a washing machine, containing one lone hydrogen atom and nothing else at all. Here is the problem that creates. Temperature, as we defined it, is the average energy of motion of particles. Take away the particles, and the definition starts to dissolve in your hands. What is the average speed of a crowd that contains one person? This is a genuine and unresolved point of disagreement among physicists, and it deserves to be stated honestly rather than smoothed over. Some argue that a near-perfect vacuum does have a temperature, defined by the motion of the few particles that remain, and by that measure, the thin gas between stars can register thousands of degrees. Others argue that the meaningful temperature is set by the radiation filling that space, which brings us back to 2.7 Kelvin. And a third group argues that neither definition applies, that asking for the temperature of emptiness is a question with no coherent answer, like asking for the color of a sound. No consensus has settled this. The number we opened with is real, rigorously measured, and universally accepted. What it is, a temperature of remains genuinely contested, which leads to something stranger still. Send a thermometer into deep space, and it will give you a reading. That reading will be stable, repeatable, and completely trustworthy. And it will not be telling you about space, it will be telling you about itself. A thermometer out there settles at whatever temperature balances the radiation falling onto it against the radiation it emits. And that balance point depends on the instrument, not the surroundings. Thermal engineers have run the numbers on this. A simple sphere placed at Earth's distance from the Sun, absorbing and emitting equally well, settles at around 279 Kelvin, roughly 6 degrees Celsius, 43 Fahrenheit. A cool spring morning. But coat that identical sphere in different materials, and its temperature ranges from about 160 Kelvin, minus 113 Celsius, 172 below 0 Fahrenheit, up past 500 Kelvin, over 226 Celsius, hotter than any oven in any kitchen on Earth. Same location, same sunlight, same vacuum, different paint. Change the color of the instrument, and you change the answer to the question. The thermometer is no longer measuring the experiment. The thermometer is the experiment. So we are left holding something unexpected. The number is real. 2.72548 Kelvin, the most precisely measured cold in existence. And yet nothing drifting alone out there, no matter how long it falls, ever settles below it. Something out in that emptiness is holding the floor in place and refusing to let anything sink further. We will have to find out what. But there is a more immediate problem, and it is the one that should be bothering you now. If space is not a material, if there is nothing out there to touch you, nothing to strike your skin, Nothing to conduct your warmth away the way that metal doorknob does. Then what exactly would happen to the heat in your body? Something must still leave. Every object in the universe cools eventually, and the vacuum is full of frozen things. There are only 3 ways heat can move from one place to another. Only 3. And out there, in the emptiness, 2 of those 3 doors are sealed shut. Conduction, convection, radiation. Those are the 3. Every transfer of heat that has ever happened anywhere, in a kettle, in a star, in the body of every creature that has ever lived, has gone through one of those 3 doors. No 4th door exists. Physics has not hidden one somewhere for special occasions. So if we want to know what actually happens to a warm body in the void, we have to walk up to each door in turn and check whether it opens. 2 of them will not. Let's be precise about what conduction actually is, because the word gets used loosely and the mechanism is beautifully simple. Put your hand flat on a kitchen countertop. Your palm is warmer than the stone, which means the atoms in your skin are vibrating harder than the atoms in the surface beneath them. Where the 2 meet, those vibrations get passed along, atom to neighboring atom, jostle by jostle, spreading outward through the material like a shove traveling down a packed crowd. Nobody in the crowd goes anywhere. The shove does. That is conduction. Energy handed along a chain of touching particles, which tells you immediately what it requires. A chain. Matter on both sides of the boundary, in contact, with no gap. Break the chain anywhere, and the transfer stops dead, because there is nothing left to pass the shove to. Now put that same warm hand out into open space. Nothing touches it. The nearest atom might be a centimetre away, and the one after that, another centimetre beyond. No contact, no chain, no handover. Door 1 is sealed. The second door is the one that actually does most of the damage to human beings on Earth. Convection is heat carried by the bulk movement of a fluid, a gas or a liquid that physically picks up warmth in one place, drifts, and drops it somewhere else. Warm air rises off a radiator and crosses your room. Warm water flows out of the Caribbean and up the Atlantic toward Europe, and it is why Britain, sitting at the same latitude as parts of Canada, has palm trees in Cornwall. Convection drives the weather. Convection moves heat from the equator to the poles. Convection is the reason this planet's temperature is spread around rather than piled up in one place. And convection is why wind hurts. Think about a fan on a summer day. The fan does not cool the air. Measure the room before and after and the thermometer barely moves. What the fan does is strip away the thin layer of already warmed air clinging to your skin and replace it continuously with fresh, cool air ready to take more from you. The fan does not lower the temperature, it raises the rate, and your nerves, which only ever measure rate, report relief. Wind chill is the same trick turned hostile. -5 with a strong wind can take heat out of you faster than -20 in perfect stillness. But every part of that mechanism depends on a fluid, something that can flow, circulate, and carry. The void has no air, no water, no currents, no drafts, no breeze, no weather of any kind. In the emptiness between the planets, nothing moves past you because nothing is there to move. Door 2 is sealed, which leaves 1. Every object in this universe warmer than absolute zero, every single one without exception, is glowing. Not glowing visibly usually, but the charge particles inside matter are in constant motion, and moving charges shed electromagnetic waves. Warm things emit, always, automatically, whether you want them to or not. Right now, sitting still, your body is shedding heat at roughly 100 watts. The same power draw as an old-fashioned incandescent light bulb, the kind that got too hot to touch. About half of that leaves you as pure infrared radiation, streaming out of your skin in wavelengths your eyes cannot register, but a thermal camera sees as clearly as daylight. You have felt this without a medium before. Stand facing a bonfire on a cold night, and one side of your face warms instantly. Not because hot air reached you, but because light did. Turn away, and it stops the moment the fire leaves your line of sight. Radiation crosses empty space perfectly. No air required, no contact required. Sunlight makes a 93 million mile journey, 150 million kilometers, through near total vacuum and arrives with enough force to burn skin. Door 3 is wide open, and it changes everything that follows. Here is the consequence, and it is not intuitive. Out there, your thermal fate has nothing to do with the emptiness surrounding you. The vacuum does not touch you, does not chill you, does not press against you. It neither takes heat nor gives it. The void is not a participant. The void is simply a corridor, a space that allows radiation to pass through unhindered in both directions. Only two things determine what happens to your temperature: what shines onto you and what you radiate away. That is the entire equation. Everything else is noise. Remember that candle burning in the cold, unheated room, the one whose warmth was leaking outward into everything around it. Take away the air, take away the floor, take away the walls, and the flame still loses heat, just more slowly, and by one route only: light. You can find the evidence for all of this in almost any kitchen, and most people have never noticed it. In 1892, the Scottish chemist James Dewar, working at the Royal Institution in London, needed to keep liquefied gases cold long enough to study them. His solution was a glass vessel inside another glass vessel, with the air pumped out of the gap between them. That evacuated gap kills conduction and convection at a stroke. No chain of particles to carry heat in, no fluid to circulate it. He then silvered the inner walls so that radiation, the one remaining route, would bounce back instead of passing through. We call the domestic version a thermos. It keeps your coffee hot for hours using nothing but the deliberate removal of 2 of the 3 doors. Now hold that thought and turn it inside out. Space is a thermos. Not a freezer, a thermos. The same vacuum that keeps your coffee hot is the vacuum surrounding every object out there, which means a warm body in space does not lose heat quickly, it loses heat slowly, and this demolishes something almost everyone has seen on a screen. The image is familiar: a body exposed to vacuum, frosting over within seconds, limbs locking, eyes crystallizing. It is dramatic. It is also physically impossible. Freezing that fast requires a fast heat loss mechanism, and the only fast mechanisms are the 2 that space does not have. With conduction and convection both gone, a human body in vacuum sheds warmth by infrared emission alone. The same slow trickle that leaks out of you every night in bed. Body heat would drain over minutes and hours, not moments. The moisture on your eyes and tongue would vaporize, and that evaporation would produce a genuine local chill. But the core of you? The core would stay warm long past the point where any of it mattered, because something else would have killed you first. Before we get to what, one more fact deserves to be sat with, because it reverses the entire premise most people carry. The dominant thermal danger during a spacewalk is not freezing, it is overheating. An astronaut inside a sealed suit is a 100-watt heat source wrapped in insulation, working hard, with no air around them to carry anything away. The heat has nowhere to go, so beneath every spacesuit, worn directly against the skin, sits a garment threaded with roughly 300 feet, around 90 meters, of fine tubing carrying chilled water. That water absorbs the astronaut's own body heat and hands it to a device in the backpack that dumps it overboard in the only way physics permits, by turning water to ice, letting the ice sublimate straight to vapor, and venting that vapor into the vacuum. The most advanced garments ever built for the coldest environment humans have entered are, first and foremost, refrigerators. That said, the picture is not one-sided, and honesty matters here. Astronauts do report genuine cold, usually in the fingers and toes, where blood flow is limited and thin gloves sit against equipment in deep shadow. NASA has fitted heaters into glove fingertips for exactly this reason. The extremities can chill while the torso is struggling to shed heat. Both problems exist at once, in the same suit, on the same person. But the system as a whole is built to reject warmth, not to trap it. So what does end a life in vacuum? 3 things, and cold is not among them. The first is hypoxia, simple oxygen starvation. Useful consciousness lasts somewhere in the range of 10 to 15 seconds. The second is expanding gas. Any air still in your lungs would rush outward as the pressure vanished. Hold your breath, and that expansion tears delicate lung tissue apart, which is why the training instruction is the exact opposite of instinct. Exhale. The third has a name most people have never heard: ebulism. Here is what it means. Water does not boil at a fixed temperature. It boils when the pressure pushing down on it drops low enough. That is why water boils cooler in a mountain town than at sea level. Keep lowering the pressure, and the boiling point keeps falling. At about 6.3 kilopascals, roughly 1/16 of the pressure you are sitting in, water boils at 37 degrees Celsius, 98.6 Fahrenheit, body temperature. That threshold has an altitude, around 19 kilometers, 63,000 feet, roughly twice as high as a passenger jet cruises. Above that line, named the Armstrong limit, after the American aviation physician Harry Armstrong, the liquid on your tongue, in your eyes, and lining your lungs will begin to boil, not because it is hot, but because nothing is left to hold it down. We know precisely what that feels like, because a man survived it and described it. On December 14, 1966, at NASA's facility in Houston, a spacesuit technician named Jim LeBlanc sealed himself into an early lunar suit prototype and entered a vacuum chamber for a routine leak test. Place yourself inside that chamber with him. The pumps have been running, the air is gone, the suit is holding at 3.8 pounds per square inch, about a quarter of the pressure at sea level, and it is doing its job perfectly. Then a pressurization hose slips loose. The suit falls to 1/10 of a pound per square inch in under 10 seconds. That is roughly 1/150th of the pressure around you right now. Effectively the vacuum of an altitude of 120,000 feet, over 36 kilometers up. He stayed conscious for about 14 seconds. 16 heartbeats. In his own account, the last thing he remembered was stumbling backwards and feeling the saliva on his tongue begin to bubble. Colleagues watching through the glass got him back. A technician in an oxygen mask reached him within roughly half a minute, and a chamber that normally takes 30 minutes to bring back to sea level pressure was repressurized in a small fraction of that. LeBlanc regained consciousness before the doctor reached him. He walked away with an earache. Not frostbite, not frozen tissue, not a single lasting injury. An earache. And notice what his body did not do, because the folklore gets this exactly backwards. His blood did not boil. It could not. Blood sits inside a closed circulatory system, held under pressure by vessel walls and the elasticity of skin. A pressure vessel you were born wearing. Only fluids directly exposed to the vacuum vaporize. Saliva, tears, the film lining the lungs. The skin holds. The body does not burst, does not explode, does not shatter. The horror of vacuum is real, but it is a horror of pressure and oxygen, not of temperature. 5 years later, the same physics took 3 lives, and the record of what happened is unambiguous. Cosmonauts Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev had just completed 23 days aboard Salyut 1, the first space station ever occupied. On June 30th, 1971, as their Soyuz 11 capsule separated for re-entry, a pressure equalization valve was jolted open at an altitude of 168 kilometers, 104 miles. The cabin air escaped in seconds. They were not wearing pressure suits. The capsule flew a textbook descent, deployed its parachute, and touched down on target in Kazakhstan. Recovery crews reached an intact spacecraft and opened the hatch to find the crew dead. They remain the only human beings to have died in space. The cause was asphyxiation from depressurization, not cold. In a warm, sealed cabin, with only radiation available to carry heat away, temperature was never the killer, and the Soviet program's response was to fit pressure suits for launch and re-entry from then on. Every crewed spacecraft since has followed that lesson. So, we arrive somewhere strange. Space cannot flash freeze a body. It has no mechanism to do so. The single door that remains open works slowly, quietly, and in both directions, and the engineering that keeps astronauts alive is mostly devoted to getting rid of heat, not holding on to it. Every mechanism that makes cold feel like cold has been removed. And yet, sensors on the shadowed surfaces of a spacesuit have measured temperatures below minus 170 degrees Celsius, minus 274 Fahrenheit. On the sunlit side of that same suit, at that same instant, the outer material can climb above the boiling point of water. Same suit, same moment, separated by the width of a human body. If the void cannot chill anything quickly, and the emptiness contributes nothing at all, what on earth is producing those numbers? The answer is not the void, the answer is the sun. At the distance Earth orbits, sunlight arrives with a measured intensity of about 1,361 watts on every square meter facing it. Hold that number for a second, because on its own it means nothing. So make it physical. The electric space heater you might put beside a desk in winter draws around 1,500 watts. Sunlight in orbit delivers nearly that much energy onto every single illuminated square meter, as though someone had pressed a running heater flat against every lit patch of a spacesuit and left it there. Nothing softens it, no atmosphere to scatter it, no cloud to break it, no air to carry the excess away. So the sunlit side of a spacewalking astronaut climbs. NASA rates its suits for surfaces reaching about 250 degrees Fahrenheit, roughly 121 Celsius. Hot enough to boil water and keep going, and the shaded side at the same instant on the same suit radiates its warmth away into an empty sky and falls to around minus 250 Fahrenheit, minus 157 Celsius, more than twice as far below freezing as the coldest air ever recorded on this planet, in deeper shadow, shielded even from Earth's own faint warmth that goes further still, close to 300 Celsius degrees of difference, 500 Fahrenheit degrees, across the width of one human body. Here is where most people misunderstand what those numbers mean. Space does not have a hot temperature and a cold temperature. Space is not switching between them. Only one thing is happening out there, a single radiation source pouring energy in one direction, and everything we call cold is simply the region that source does not reach. Shadow in space is not a cool place. Shadow is an unlit place, and in the absence of light, an object does the only thing physics allows. It keeps radiating its own warmth outward, endlessly, into a sky that sends nothing back. That distinction is the whole engineering problem. You can test the opposite case on the next warm afternoon, and the result will feel so ordinary that its strangeness slips past. Step out of direct sunlight into the shade of a building. Your skin cools immediately, the radiation stopped, but the air around you is essentially unchanged. Put a thermometer in the sun and another in the shade, and the difference is often a degree or two, no more. Why? Because the atmosphere refuses to hold a gradient. Air molecules collide, mix, drift and rise, endlessly stirring warmth from where it landed to where it did not. 5,000 trillion tons of gas in constant motion, smoothing every hotspot toward the average. Earth wears a thermal blanket, and the blanket is the air itself. Now remove it. Not the sunlight, just the air. Every shadow on this planet instantly becomes a cliff instead of a cool spot. The lit side of a rock scorches, the dark side, a hand's width away, plunges. A garden wall would have a summer face and a winter face at the same moment. That is exactly what orbit is like. A single bolt on the outside of a spacecraft can be blistering on the side that sees the sun, and deeply frozen on the side that does not, with barely a centimetre, less than half an inch, of metal between the two. Engineers do not treat that as an exotic case. They treat it as Tuesday. For the cleanest demonstration of what an airless world does, look up on the next clear night. The Moon has no meaningful atmosphere. Its wisp of gas is so thin that a cubic centimetre of Earth's air holds around 100 trillion times more molecules than the same volume at the lunar surface. Nothing there mixes, nothing carries. Sunlight lands, and the ground alone decides what happens next. Near the lunar equator at midday, the surface climbs above 120 degrees Celsius, over 250 Fahrenheit. That heat does not last a few hours. The Moon turns so slowly that daylight at any given spot runs for roughly 14 Earth days. 2 solid weeks of that heat are pressed against the ground without a single night to interrupt it. Then the sun sets, and nothing replaces it. Temperatures collapse to around -133 Celsius, -208 Fahrenheit, and keep sinking through 14 more days of darkness, approaching -170 by the hour before dawn. For a moment, imagine you're standing there in a suit at the Terminator line where lunar day meets lunar night. Ahead of you, ground that has been baking for 2 weeks. Behind you, ground that has been radiating into blackness for 2 weeks. You could walk from one to the other in a few strides. The sky above both is identically black, identically silent, and utterly indifferent to which side you choose. The harshest deserts on Earth might swing 50 or 60 degrees between noon and dawn. The Moon swings close to 300, and at the lunar poles, that same absence of air produces something genuinely extraordinary. The Moon's spin axis is tilted barely 1.5 degrees, which means sunlight at the poles never rises far above the horizon. It grazes, and inside certain deep craters, the floor has not received a single photon of direct sunlight in what models suggest may be billions of years. In 2009, NASA's Lunar Reconnaissance Orbiter carried an instrument called Diviner, a radiometer designed to map the temperature of the lunar surface, into polar orbit, and timed its measurements for the depths of polar winter night. On the southwestern floor of Hermit Crater, near the North Pole, Diviner recorded 26 Kelvin, -249 degrees Celsius, -415 Fahrenheit, the coldest surface ever measured anywhere in the solar system. Think about what that ranking actually means. Pluto, 4.5 billion kilometers out, roughly 2.8 billion miles, a world so distant the sun there looks like a bright star, has a surface temperature around -230 degrees Celsius. Hermit Crater is nearly 20 degrees colder than Pluto, and it sits on a body we can see with the naked eye from a back garden. No refrigeration produced it, no exotic physics, just shadow, held perfectly still for longer than complex life has existed on Earth. Similar readings turned up at the southern edges of Peary and Bosch craters, and the permanently shadowed site inside Cabeus, where NASA deliberately crashed the L-Cross spacecraft in 2009 to kick up debris for analysis, holds an average annual temperature of about 37 Kelvin. These places have a name in the literature: cold traps. A cold trap works exactly the way a drain in a basement works. Water vapor wandering across the lunar surface, delivered over aeons by comet and asteroid impacts, moves until it reaches somewhere cold enough that it can never leave again. At 26 Kelvin, water does not merely freeze. It becomes effectively immobile, locked in place for geological time, which turns the coldest ground in the solar system into something unexpectedly valuable. Water means drinking water, breathable oxygen, and rocket propellant. The difference between visiting the Moon and staying there. NASA's Artemis program is targeting the lunar South Polar region specifically in candidate landing zones chosen for their proximity to these permanently shadowed regions. The coldest known place we have ever measured may become the most useful piece of real estate off Earth. But even here, notice something. Every one of those numbers describes ground. Regolith, a physical thing that absorbs sunlight, holds it, and radiates it away. Lift a thermometer 1 meter above the sunlit lunar surface, and it would settle at a different reading entirely, because now it is balancing direct sunlight, plus the infrared glow rising off the hot ground beneath it, against whatever it emits from its own surface. Raise it higher, tilt it, paint it white, and the number changes again, which is why engineers who build spacecraft never once ask what the temperature of space is. They ask a different question, not how cold is it out there, but what is the balance? Every object in orbit sits inside a ledger with 5 entries: energy arriving directly from the sun, energy arriving as sunlight bounced off a nearby planet. Earth reflects roughly 1/3 of what hits it, and that reflected light warms anything in orbit above it. Energy arriving as infrared, glowing up from the warm planet below. Energy generated internally by every computer, pump, light, and human on board. And energy leaving, radiated outward from the surfaces. Balance those 5 and the object holds steady. Let one shift and the temperature moves. That is the whole discipline. Not fighting cold, managing a ledger. The tools are unglamorous and utterly essential. Multi-layer insulation, the crinkled gold foil you see wrapping spacecraft, which is not one blanket but dozens of tissue-thin reflective sheets, each one bouncing radiation back before it can cross. Optical coatings, chosen with the precision of a painter, because a surface that absorbs sunlight well and radiates infrared poorly runs hot, while the reverse runs cold. Heat pipes to move warmth from where it collects to where it can escape, radiators to throw it overboard, and heaters, electric heaters, for everything that would otherwise get too cold. The International Space Station runs both problems simultaneously, every 90 minutes, forever. Inside, it is a sealed box containing people, laboratory freezers, lighting, and racks of computers, all of them generating heat, none of it able to escape through air, because there is no air outside to take it. So the station pumps that waste heat into water loops, hands it across heat exchangers to loops of liquid ammonia, and sends the ammonia out to enormous white radiator panels mounted on the truss. Those panels glow in infrared, invisibly, continuously. They are the station's only exhaust pipe. Meanwhile, on the same structure, in the same minute, batteries and fuel lines and door seals and camera optics, sitting in permanent shadow, are being kept alive by electric heaters, because if they get too cold, they crack, seize, or simply stop working, cooling and heating, at once, on one machine. And every 90 minutes the station crosses from full sunlight into Earth's shadow and back again. 16 sunrises and 16 sunsets in a single day, each one a violent swing in the ledger that the thermal control system has to absorb without letting anything drift out of range. The James Webb Space Telescope took this logic and pushed it toward its limit. Webb hunts infrared light, heat radiation from the most distant galaxies ever observed, which creates a brutal problem. A warm telescope glows in exactly the wavelengths it is trying to detect. Its own body would drown the signal, the way a torch pointed at your face drowns out a candle across the room. The solution was not refrigeration. The solution was shade. Webb carries a sunshield roughly 21 meters by 14, 69 feet by 46, about the footprint of a tennis court, built from 5 separate layers of metal-coated film, the inner sheets thinner than a human hair, held apart so that heat leaking through one layer radiates sideways into the gap before it reaches the next. Across that stack, from the sun-facing side to the shaded side, the temperature drops by roughly 300 degrees. Behind it, the telescope's mirrors and near-infrared instruments cooled passively, no machinery, no coolant, just permanent artificial shadow, to somewhere near 40 Kelvin. Webb did not cool itself. Webb built itself a night and then let physics do the rest. But its fourth instrument, MIRI, the mid-infrared instrument built jointly by NASA and the European Space Agency, needed detectors below 7 Kelvin to work at all. Shade alone could not reach that. So Webb carries the one piece of active machinery in its entire optical chain, an electrically powered cryocooler, which brought MIRI down through a difficult final stage engineers called the pinch point and settled it at 6.4 Kelvin. Even that is not the record. ESA's Planck spacecraft, launched in 2009, was built to map the faint microwave glow filling the sky. And to do that, its high-frequency instrument had to be colder than almost anything in nature. Planck cooled passively to about 45 Kelvin, then handed the job to a chain of 3 active coolers, each one taking over where the last ran out, down to 20 Kelvin, then 4, then a dilution cooler using helium. 3 and helium-4 that carried the detectors to 1/10 of a degree above absolute zero. 0.1 Kelvin. Measured up from the absolute floor, the air in the room around you is roughly 3,000 times warmer than those detectors were. For the duration of that mission, Planck's high-frequency instrument was the coldest known object anywhere in space. It ran for about 2.5 years, nearly 3 times its design life, until the last of the helium was spent and the instrument warmed and its work was done. Sub-Kelvin refrigeration in space is no longer a stunt. It is now the foundation beneath modern cosmology and infrared astronomy, because the faintest signals in the universe can only be read by instruments quieter and colder than the signal itself, which brings us to something quietly astonishing hiding inside all of this engineering. Look at what those machines had to do. Planck needed 3 separate active coolers, burning power and consuming irreplaceable helium to reach 1/10 of a Kelvin. Webb needed a dedicated cryocooler to get Miri to 6.4. Passive shade, perfect shade, tennis court shade, the best we know how to build, got Webb's optics to about 40 Kelvin and no further. Turn off every cooler, remove every heater, let any object in deep space simply drift, shaded, for as long as it likes. It will not fall to 0, it will not fall to 1 Kelvin, it will slide down through the temperatures we have been describing, slow and steady, and then it will stop at 2.7 and stay there permanently no matter how long you wait. Every passive object in this universe hits the same floor. Something is holding it. So where did that floor come from? Picture a single rock drifting between the stars. Nothing touches it. Nothing shines on it. No nearby sun, no planet glowing below. It simply moves through the dark, doing the only thing an object in that situation can do, radiating its own warmth outward in every direction, forever. And it cools. It falls past the temperature where water freezes, past the point where carbon dioxide turns solid, the temperature of dry ice, cold enough to burn skin on contact. It keeps going, down past the boiling point of liquid nitrogen, the coldness that shatters a rose like glass. It slides below the temperature of liquid helium, colder than anything in a hospital or a laboratory on Earth. And then it stops. Not slows. Stops. At 2.7 Kelvin and never falls further, no matter how many millions of years you let it drift, which should be impossible. A body radiating into perfect emptiness has no reason to halt anywhere in particular. Something must be pushing back, something faint, arriving from every direction at once, filling the entire volume of the universe with a whisper of energy that will not let anything sink below it. To find out what that is, we have to go back, all the way back, roughly 13.8 billion years. And immediately, we hit a phrase that misleads almost everyone who hears it. The Big Bang was not an explosion. No fireball tore outward through empty space. No center existed, no edge, nothing for the debris to fly into, because space itself was the thing that changed. Think of dough rising in a warm kitchen with raisins scattered through it. As the dough expands, every raisin drifts away from every other raisin. Ask any raisin, and it will tell you it sits at the center of the expansion, with everything else fleeing from it. But no raisin is moving through the dough. The dough is getting bigger and carrying them all along. That is what happened. Space stretched. Everything embedded in it was carried apart. And in that first moment, everything we can now observe, every galaxy, every star, all 100 billion trillion of them, occupied a volume that models place at smaller than a single atom. The figures vary depending on which model of inflation you use, and cosmologists are honest that the earliest instance remained genuinely uncertain. But the scale of the claim survives every version of it. Compress the observable universe to something you could hide inside a hydrogen atom. That was the starting condition. Squeeze that much energy into that little room and the temperature becomes something the human mind has no handhold for. Standard models put the earliest instance at somewhere around 10 to the 27th Kelvin. Written out, 1 billion degrees. Here is the only honest way to feel that number. The hottest thing human beings have ever created sits inside CERN's Large Hadron Collider, where the ALICE experiment smashes lead ions together at 99% of the speed of light. For a fraction of an instant, that collision produces a quark-gluon plasma at around 5.5 trillion degrees. The current world record, set in 2012, roughly 100,000 times hotter than the core of the Sun. The early universe was something like 200 trillion times hotter than that. No laboratory analogue exists. No star has ever come close. We are describing a condition that has occurred exactly once and never again. Now, let the dough rise. Expansion cools, the same physics that makes a can of compressed air go cold in your hand as the gas escapes and spreads. 1 second in, the universe had fallen to about 10 billion degrees Celsius, which is still absurd. The core of our Sun, the furnace running the fusion that keeps this planet alive, sits at around 15 million degrees. The 1 second old universe was over 600 times hotter than that, everywhere, all at once with no cool place anywhere in existence. Nothing complicated could survive it. What filled that space was a plasma. Bare protons, bare neutrons, free electrons, photons of light, and neutrinos, all colliding at unimaginable speed. And the plasma was opaque. That word matters more than it sounds. Free electrons are extraordinarily good at scattering light. A photon traveling through that soup would move a vanishingly short distance before slamming into an electron and ricocheting off in a random direction, again and again and again. Imagine driving into thick fog at night. Your headlights are working perfectly. Photons are pouring out of them by the trillion, and you cannot see 3 meters ahead because every one of those photons bounces off water droplets before it reaches anything useful. The early universe was that fog, filling everything. Light existed from the very beginning. Light simply could not go anywhere. Between roughly the first second and about 20 minutes, something extraordinary happened, and then the door closed on it permanently. The temperature dropped into a narrow window where protons and neutrons could stick together instead of being instantly blasted apart. Physicists call this Big Bang nucleosynthesis, the universe's only period of large-scale element manufacture. Protons and neutrons fused into deuterium, heavy hydrogen, 1 proton and 1 neutron bound together. Deuterium fused into helium-4. Tiny traces of lithium formed at the edges of the process, and then the window shut. Expansion kept cooling the plasma, the collisions lost the energy needed to fuse anything, and the cosmic reactor switched off after roughly 20 minutes of operation. Less time than it takes to boil a pot of soup. What it left behind was a fixed ratio, locked in for all of cosmic history, about 75% hydrogen and 25% helium by mass, with everything else a rounding error. That number never went away. The hydrogen in a simple glass of water is not made by any factory. Nearly all of it is primordial, forged in the first 20 minutes of time and simply relocated ever since. You can hold in your hand matter assembled before the universe was half an hour old. Here is what makes this more than a nice story. It was a prediction, and predictions can fail. If the Big Bang model was right, then the very oldest stars formed from gas that had not yet been polluted by generations of stellar nucleosynthesis should still show that primordial recipe in their light. Roughly 3/4 hydrogen, roughly 1/4 helium, trace deuterium at about 1 part in 100,000. Astronomers went and looked, and the measured abundances of hydrogen, helium and deuterium in ancient stars match the predicted values closely. One of the genuine pillars holding up modern cosmology, and one of the reasons the model is taken as seriously as it is. But not everything matched. Lithium-7 is wrong. Not slightly wrong. wrong by a factor of about 3. Standard Big Bang nucleosynthesis, calibrated using the same measurements that get hydrogen, helium, and deuterium right, predicts substantially more primordial lithium-7 than astronomers actually find in old, metal-poor halo stars. The observed abundance sits at roughly a third of the prediction. Some analyses put the gap as high as a factor of 4. Cosmologists call it the lithium problem, and it has resisted solution for more than 2 decades. 2 broad camps have formed, and both are serious. One argues the fault lies in the stars, not the model, that lithium is fragile, and that internal transport processes inside these ancient stars, collectively called atomic diffusion, have quietly sunk lithium out of the visible surface layers over billions of years. Evidence for this has been accumulating, and some researchers now think stellar physics may account for the whole discrepancy. But modelling the interior mixing of a star from first principles remains difficult, and the quantitative picture is not finished. The other camp argues something is missing from the physics itself, some particle or process operating during those 20 minutes that standard models do not include. A third possibility is quieter and more mundane, that the nuclear reaction rates governing lithium's creation and destruction were simply mismeasured. Teams have been steadily nailing those rates down in the laboratory, removing ambiguities one at a time. No consensus has settled it. The evidence currently leans toward the stellar explanation, but the problem remains genuinely open. And every so often, in the history of physics, a stubborn factor of 3 has turned out to be the loose thread on something much larger. Whatever the answer, the element-making ended, and what followed was almost unimaginably monotonous. For hundreds of thousands of years, the universe just sat there and glowed. Above 3,000 Kelvin, everywhere, uniformly. A furnace with no walls and no outside. Still opaque. Still fogged with free electrons. Nothing forming, nothing collapsing. No stars, no structure, no darkness anywhere at all. And then, at roughly 380,000 years, the temperature crossed a threshold. Below about 3,000 Kelvin, photons no longer carried enough punch to knock electrons away from nuclei the instant they got close. So the electrons stayed. For the first time in the history of the universe, negatively charged electrons settled into orbit around positively charged nuclei, and neutral atoms came into existence. Hydrogen, helium, the first atoms that had ever been. Physicists call this recombination, which is strictly the wrong word, since nothing had ever been combined before. The name is a historical accident that stuck, and the consequence was immediate and total. Neutral atoms are almost transparent to light in a way free electrons never are. The moment the electrons bound, the scattering stopped, and the fog that had filled all of space since the beginning of time cleared almost instantly. Every photon that had been ricocheting endlessly through the plasma suddenly found nothing in its way, and it left, in a straight line, into a universe that had just become see-through. That boundary has a name, the surface of last scattering, the place where light was deflected for the final time before beginning a journey that, for some of those photons, is still going on right now. It is the oldest light that can ever exist. Not the oldest light we have found, the oldest that can be found. Look further back, and you are looking into the fog, and the fog does not let anything through. That surface is a wall built into the structure of time itself. Now place yourself inside that moment, 380,000 years after the beginning. 3,000 Kelvin is roughly the temperature of the filament inside an old incandescent light bulb, that familiar warm orange glow. So the entire universe was that colour, not a glow coming from somewhere, a glow coming from everywhere. Look in any direction and you would see the same dull orange-red light at the same brightness, with no source and no origin, no sun, no horizon, no shadows, because shadows require a direction for the light to come from, and here the light came from all directions equally. You could not cast a shadow. You could not find a darker patch to move toward. Every cubic centimetre of the universe, including the space occupied by your own body, was filled with the same faint fire, and it was warm. 3000 Kelvin is hotter than molten iron. That was the sky, everywhere, for everyone, uniform to within about 1 part in 100,000. Those photons set off, and the dough kept rising. Since that moment, space has expanded by a factor of roughly 1100. And here is the crucial part. A photon traveling through stretching space stretches with it. Its wavelength gets pulled longer, and a longer wavelength means lower energy, which, for a bath of radiation, means a lower temperature. The light that left the surface of last scattering peaked at under a micrometer, a wavelength smaller than a bacterium, sitting right at the edge of what human eyes can see. Today, that same light peaks at just over a millimeter, roughly the thickness of a credit card. The temperature followed it down by exactly the same factor. 3000 Kelvin divided by about 1100 gives 2.725. That is the answer. That is what stops the drifting rock. The floor beneath everything cold in this universe is the cooled remains of the fire that filled it. And notice what has not changed. The universe is still glowing, exactly as it did then, in every direction, from every point. Nothing has been extinguished. The light of that first moment is still passing through this room right now, through the walls, through your body, at this exact second. Several hundred photons of it, in every cubic centimeter of space around you. We simply cannot see it. Human eyes evolved to catch a narrow band of wavelength thrown off by a yellow star, and the primordial glow was stretched clean out of that band long before there were eyes to miss it. The sky did not go dark, the sky went invisible, which leaves us with an idea worth sitting with. Expansion has been acting as a refrigerator since the very beginning, not by removing heat, but by diluting it, spreading the same fixed quantity of energy across an ever-growing volume until the temperature everywhere collapses toward nothing, and the total budget was set at the start. Every joule of heat in this universe traces back to that inheritance. Stars look like they contradict this. A star seems to be making energy, pouring out light that did not exist before. But fusion creates nothing. A star converts matter that was already there into energy that was already accounted for, and then radiates it into expanding space, where it thins and reddens and never comes back. Nothing tops the universe up. The fire was lit once, which also means the floor is not fixed. 2.7 Kelvin is simply where that inheritance stands today, and as space continues to stretch, that number will keep falling slowly for as long as expansion lasts. But hold on, because everything just said rests on an extraordinary claim that a faint glow filling all of space is the direct, measurable remnant of an event 13.8 billion years ago. That is not the kind of thing anyone should accept, because it sounds elegant. So how was it ever proven? By accident. That is the honest answer. The most important measurement in the history of cosmology was made by two men who spent the better part of a year trying to get rid of it. At Bell Telephone Laboratories, on a hill in Holmdel, New Jersey, stood a horn antenna, a great aluminium funnel about 15 meters long, roughly 50 feet, built not for astronomy but for Project Echo, an early experiment in bouncing radio signals off metallic balloons in orbit. By the early 60s, the antenna had been freed up for research, and two radio astronomers, Arno Penzias and Robert Wilson, took it over. Their work required knowing exactly how much noise the instrument itself produced. Every receiver hums. The job was to account for every source of that hum, subtract it, and be left with a clean zero. They never got to zero. In May of 1964, the chart recorder showed more microwave power arriving from the sky than either man could explain. So they went hunting. They checked for interference from New York City, 30 miles up the coast. They looked for radar signals, for nuclear test fallout, for faults in the wiring. They took the receiver apart and recalibrated it. They taped over every seam in the horn's aluminium joints, in case radiation was leaking in through the rivets. And then there were the pigeons. A pair had nested inside the throat of the antenna and coated its interior with what Penzias, with a certain dry precision, described as a white dielectric material. The two future Nobel laureates climbed into the horn and scrubbed it out by hand. The noise dropped slightly and stayed. When every known contribution had finally been subtracted, an excess remained, the equivalent of a thermal source at about 3.5 Kelvin, give or take 1 degree, less than 4 degrees above the absolute floor of reality. But the number mattered less than the behavior. That hiss was identical in every direction they pointed the antenna. It did not change with the seasons. It did not change with the hour of the day, or with the rotation of the Earth, or with where the Milky Way sat in the sky. Nothing on this planet, and nothing in this galaxy, behaves like that. Whatever it was not coming from anywhere. It was coming from everywhere. Here is where the story cracks open. Roughly 30 miles from Holmdel, about 50 kilometers, a group at Princeton University led by Robert Dicke had been working through exactly this idea. If the universe began in a hot, dense state, Dicke reasoned, some residue of that heat should still be detectable today. Jim Peebles had done the theoretical work, estimating what temperature that residue should have. Peter Roll and David Wilkinson were, at that very moment, building an antenna to go and find it. The connection came through a conversation. Penzias mentioned his troublesome noise to Bernard Burke at MIT. Burke had heard about Peebles's calculations and pointed Penzias toward Princeton. Penzias picked up the phone and called Dicke. Imagine being in that room. Dicke listening, understanding faster than he wants to, then hanging up and turning to the men building his instrument. He drove out to Holmdel to see the data himself. The Bell Lab signal had every property his theory demanded. Princeton had been scooped by a receiver that was never meant to look at the sky at all. The two groups handled it with unusual grace. In 1965, they published side by side in the same issue of the Astrophysical Journal, Penzias and Wilson reporting the measurement in deliberately understated language, Dicke's team supplying the interpretation in a companion paper. That interpretation was this: the noise was the relic heat of the beginning, cooled by expansion, arriving after roughly 13.8 billion years of travel. Penzias and Wilson shared the Nobel Prize in Physics in 1978, except the measurement was crude, and everyone knew it. 3.5 Kelvin, plus or minus a full degree, is not a precision result, and the reason was sitting directly overhead. Earth's atmosphere absorbs and emits at exactly the wavelength the signal arrives on. Trying to measure the temperature of the universe from the ground is like trying to hear a whisper from the next room while standing beside a running tap. To do it properly, the instrument had to go above the air. On November 18, 1989, NASA launched COBE, the Cosmic Background Explorer. COBE returned 2 results. Both of them reshaped cosmology. The first came from an instrument called FIRUS, which compared the sky's spectrum against a reference black body carried on board. A black body is simply an object whose glow depends on nothing except its temperature. No chemistry, no composition, no history. Heat a lump of iron and a lump of clay to the same temperature in a sealed furnace, and their glow becomes indistinguishable. Pure thermal light with a distinctive shape. Big Bang cosmology predicted the sky should show that shape exactly, because the early universe was a sealed furnace with nothing outside it. The measurement came back within weeks. The cosmic microwave background matches a perfect blackbody curve to better than 50 parts per million. To picture what that means, draw the theoretical curve on a page, then plot the measured data on top of it. Every measured point falls inside the thickness of the drawn line. The error bars have to be artificially enlarged just to be visible on the graph. No object in nature had ever been shown to be that thermally pure. Not a star, not a furnace, not anything built in a laboratory. The most perfect blackbody ever recorded is the sky itself, and the temperature 2.725 Kelvin, with an uncertainty of about 1/1000th of a degree. The second result came from a different instrument, and it took years of careful analysis to trust. COBE found that the glow is not perfectly smooth. Across the sky, tiny variations exist. regions very slightly warmer and very slightly cooler, at the level of about 1 part in 100,000, roughly 30 millionths of a degree. That level of uniformity is difficult to overstate. Picture a road 2 kilometers long, about 1.25 miles, whose surface never rises or falls by more than 2 centimeters, under an inch, along its entire length. That is how smooth the early universe was. But those 2 centimeters are the reason anything exists. Slightly denser regions pulled in slightly more matter. More matter meant stronger gravity, which pulled in more still. Over hundreds of millions of years, those faint density variations collapsed into the first stars, the first galaxies, the great filaments of the cosmic web, and eventually into a rocky planet with an atmosphere and an ocean. Every structure in the universe grew from imperfections 100,000th of a degree deep. Their origin is stranger still. The leading explanation says those ripples began as quantum fluctuations, the tiny, unavoidable jitter of energy at subatomic scales, which were then stretched to cosmic proportions during the universe's first fraction of a second. Randomness at the smallest scale physics permits, blown up until it became the blueprint for everything. COBE saw the sky through a considerable blur. Its resolution was about 7 degrees, meaning the smallest feature it could distinguish covered 14 full moons side by side. NASA launched WMAP on June 30th, 2001 to fix that. Parked 1.5 million kilometers from Earth, about 1 million miles, on the side facing away from the Sun, WMAP mapped the same sky at roughly 35 times COBE's angular sharpness. The result became famous as the baby picture, the universe as it looked at 380,000 years old, rendered in fine enough detail to extract numbers from. MAP put the age of the universe near 13.7 billion years, and for the first time delivered a genuine inventory of what the universe is made of. ESA's Planck mission, launched in 2009, went further still, mapping the whole sky in 9 separate frequency bands, which allowed the team to identify and subtract contaminating glow from our own galaxy with unprecedented care. Planck produced the sharpest maps of the primordial sky ever made. Its refined figures, an age of about 13.8 billion years, and a composition budget that should stop anyone who hears it properly. Ordinary matter, atoms, everything on the periodic table, every star and planet and living thing, makes up roughly 5% of the universe. Dark matter, which we detect only through its gravity and have never identified, accounts for about 27%. Dark energy, which appears to be driving cosmic expansion and which we understand less well still, accounts for the remaining 68%. Everything you have ever seen, touched, tasted, or built an instrument to detect belongs to the 5%. But the maps contained a puzzle that had been quietly bothering cosmologists since before COBE flew. Take 2 patches of sky on exactly opposite sides, one directly overhead, one directly beneath your feet on the other side of the planet. Their light has traveled 13.8 billion years to reach us. They have never been in contact. Light has never had time to cross from one to the other, not once in the entire history of the universe. And yet their temperatures match to within 1 part in 100,000. How? 2 regions cannot agree on a temperature without exchanging energy. Any more than 2 sealed rooms on opposite sides of a city can settle at the same temperature without something passing between them. Cosmologists call this the horizon problem, and for years it sat there like a crack in the wall. In 1980, the physicist Alan Guth proposed a solution that sounded outrageous and has since become foundational: inflation. The idea, in the first unimaginably brief instant, space expanded by a factor of at least 10 to the 26th, and it did so in something like a trillionth of a trillionth of a trillionth of a second. Apply that magnification to a marble 1 centimeter across, and the marble becomes roughly 100 million light-years wide, larger than our entire local group of galaxies, in less time than any process we can name, and that solves the puzzle by reversing it. Those opposite patches of sky were in contact, snugly, intimately in contact, close enough to equalize, before inflation flung them apart faster than light could ever follow. They agree on temperature because they once touched. The maps hold something else too, and this is the part that turns cosmology into a precision science. Before the fog cleared, the plasma filling the universe could carry sound. Gravity pulled matter into the denser regions. Radiation pressure pushed back out. The whole medium rang like a struck bell. Actual pressure waves, moving through actual material. When the universe went transparent, those waves froze in place, and their pattern is still printed across the sky. Cosmologists call them baryon acoustic oscillations. Frozen sound, 13.8 billion years old. Read the pattern, and it gives up secrets. The angular size of the first and largest peak reveals the geometry of space itself, and it comes out flat to within a fraction of a percent, meaning two parallel light beams stay parallel forever. The relative heights of the successive peaks reveal how much ordinary matter was present versus dark matter, and they show dark matter outweighing ordinary matter by roughly 5-1. None of that was assumed. All of it was extracted from ripples in a temperature map. Still, a skeptical viewer should push back at this point, because everything so far comes from one signal measured today. Where is the independent check? The prediction is simple and brutal. If the glow really is relic heat cooled by expansion, then looking further away, further back in time, should reveal it hotter by a precisely calculable amount. Astronomers have tested this. They measure the temperature of the background at high redshift by watching how it excites molecules in distant gas clouds, and by studying how the light is distorted passing through hot galaxy clusters, the Sunyaev-Zeldovich effect. The measured temperatures rise with distance, matching the predicted relationship. The universe was demonstrably hotter in the past, not inferred, observed, and yet the picture is not clean. Two problems refuse to go away. The first sits in the constellation Eridanus. On the maps, a large region appears colder than the surrounding sky, by more than the standard model comfortably allows. Cosmologists call it the cold spot, and its statistical significance sits at roughly the 3 sigma level, meaning a random fluke would produce something like it perhaps once in a few hundred tries. Suspicious, well short of proof. Astronomers found a real structure aligned with it, the Eridanus supervoid, an enormous underdense region confirmed independently through gravitational lensing by the Dark Energy Survey. A photon crossing a vast void loses a little energy on the way out, so a void should cool the light passing through it. But the arithmetic falls short. Under the standard model, the supervoid accounts for only about 10 to 20% of the observed temperature depression, so the debate remains open. Some argue the remainder is simply a statistical accident. Look at enough sky and rare patterns appear. Others propose a cosmic texture, a hypothetical defect left over from a phase transition in the very early universe. Others suspect the void's effect has been underestimated because something in our model of dark energy is incomplete. No consensus exists. Deeper surveys of that region are the way this gets settled. The second problem is larger, and it goes to the heart of the thermal story. Two methods measure how fast the universe is expanding today. The first reads it out of the primordial sky maps. Run the standard model forward from the fluctuation pattern, and you get an expansion rate near 67.4. The second measures it directly and locally by climbing a ladder of distance markers, pulsating Cepheid stars, then exploding stars in more distant galaxies, and reading how fast those galaxies recede. That method gives about 73. The gap is around 8%, small enough to sound trivial, large enough that, at the precision both sides now claim, they cannot both be right. For years, the obvious suspect was the local method, specifically the worry that Cepheid stars in crowded galactic centers were contaminated by neighboring starlight in Hubble's images, inflating the result. JWST tested that directly, resolving over 1,000 Cepheids at far higher resolution, and Adam Rees and colleagues rejected crowding as the explanation at 8 sigma confidence. The local measurement held. The disagreement now stands near 5 sigma, a probability of roughly 1 in 3.5 million that it is chance. Wendy Friedman's group has pursued a different rung of the ladder, using the tip of the red giant branch and a newer method based on carbon-rich giant stars. Their results tend to land between the two camps, and they argue the local measurements carry more uncertainty than the headline figures suggest. Rees's team disputes that reading of the same data. That argument is live, ongoing, and conducted between serious people who have spent careers on it. What it means, if the tension is real, matters here more than anywhere. Because the sky maps do not measure expansion directly. They measure a temperature pattern and then convert it into a history using assumptions about what the universe contained and how it cooled. If the conversion disagrees with what we see happening locally, then one of those assumptions is wrong, and the thermal history that produced the 2.7 Kelvin flaw is incomplete, in some way we have not yet identified. The number itself is not in doubt. The path that led to it might be. So the afterglow is proven, measured to 5 decimal places, verified across redshift, mapped by 3 generations of spacecraft, and still holding 2 unresolved cracks that nobody can close. And that faint relic sets the floor. 2.7 Kelvin everywhere, holding the temperature of every drifting rock and every dead star and every abandoned spacecraft in the observable universe. No passive object escapes it. Nothing cools below it on its own. Which raises the obvious question, the one that would have to be answered before any of this could be called complete. In a universe with a flaw that firm, is there anything at all that manages to break it? One thing does. But before we go to it, we should look properly at what the universe puts on the other side of the ledger, because the objects that defy the cold in the ordinary direction are worth understanding first. Start with the one you have felt on your skin. The sun's visible surface runs at roughly 5,500 degrees Celsius, near 10,000 Fahrenheit. Hot enough that no solid material we know of could exist there for an instant. But the surface is the cool part. Down in the core, the temperature reaches about 15 million degrees Celsius, and at that temperature atoms no longer exist in any recognizable sense. Electrons have been stripped away entirely. What remains is bare nuclei, moving fast enough to slam together against their own electrical repulsion and fuse. Every second, that process converts roughly 4 million tons of matter into pure energy. Not burns it, converts it, mass ceasing to be mass and leaving as light. 4 million tons is about 11 Empire State Buildings, deleted from existence every second since before this planet had oceans. The energy that escapes crosses 150 million kilometers, 93 million miles, and arrives here about 8 minutes later, which means the warmth on your face is always 8 minutes old. And here is the part that reframes everything. Our star is unremarkable. Middle-aged, medium mass, an ordinary yellow dwarf. In the census of stars, it is not special in any direction. Look at Rigel, the brilliant blue-white star marking Orion's foot. Its surface exceeds 11,000 degrees Celsius, roughly twice the temperature of the sun's surface, which is why it burns blue rather than yellow. The color of a star is not decoration. Color is temperature, written in light. Inside stars like that, fusion runs in nested shells, like the layers of an onion. Hydrogen burning in the outermost, then helium beneath it, then carbon, then oxygen, each layer hotter and denser than the one above. But that intensity costs everything. Stars above roughly 100 times the sun's mass live only a few million years. Put that against a human sense of time. If the sun's 10 billion year lifespan were compressed into a single year, one of those monsters would exist for about 2.5 hours. Born, burning, gone before lunch. Now go the other way, and something stranger appears. Red dwarfs run at around 3,000 degrees Celsius at the surface, barely half the sun's temperature, glowing dull red, the color of a dying ember. They are small, dim, and utterly dominant. Roughly 70% of the stars in the Milky Way are red dwarfs. Some estimates run higher, and not one of them is visible to the naked eye, not a single one. Every star you have ever looked up at and admired belongs to the rare, bright minority. The actual majority of our galaxy is invisible from a back garden. Their fuel consumption is so miserly that their lifespans stretch into the trillions of years. Sit with the consequence of that. The universe is 13.8 billion years old. The lowest mass red dwarfs have lifespans over 1,000 times longer than that, meaning the oldest ones in existence have burned through barely 1% of their fuel. Every red dwarf that has ever ignited is still burning. Not one has ever died. In the entire history of the universe, that category of star has a death toll of 0, which makes them the natural place to look for life, and the site of a genuine and unresolved argument. The case against is substantial. A red dwarf is so dim that a planet must huddle close to stay warm, often closer than Mercury sits to our Sun. At that distance, tidal forces almost certainly lock the planet, so one hemisphere faces permanent day and the other permanent night. Worse, red dwarfs are magnetically violent, throwing out flares of ultraviolet and X-ray radiation, powerful enough to strip a planet's atmosphere away over geological time. The case for is equally serious. Modern three-dimensional climate models suggest that even a modest atmosphere generates winds and ocean currents capable of redistributing heat around a tidally locked world, preventing the night side from freezing solid. And the numbers are overwhelming. If 70% of stars are red dwarfs and they last for trillions of years, then the vast majority of all habitable real estate and all habitable time in this universe belongs to them. No consensus exists. JWST is now measuring the atmospheres of real planets around real red dwarfs. TRAPPIST-1, Proxima Centauri, and those observations will settle it in a way argument never could. Stars are not the hottest things out there, not remotely. When gas spirals into a black hole, it does not fall straight in. It forms a disk, and friction within that disk, layers of gas grinding past each other at a substantial fraction of light speed, heats it savagely. Around a stellar mass black hole, the inner disk reaches tens of millions of degrees, hot enough to glow in X-rays rather than visible light. Around a supermassive black hole, the disk itself is actually cooler, radiating mostly in ultraviolet. But wrapped around both sites something else, a thin, turbulent cloud of plasma that astronomers call the corona, threaded by magnetic fields, and NASA modelling puts its temperature near 1 billion degrees. That is roughly 60 times hotter than the centre of the Sun, in a region of near vacuum, orbiting at velocities approaching the speed of light. And even that is not the peak. When a massive star runs out of fuel, its core is iron, and iron cannot be fused for profit. Fusion stops, support vanishes, and an iron core roughly the size of the Earth collapses. Now picture the numbers on that. The infalling material reaches about 1/4 of the speed of light, 70,000 kilometers per second, around 45,000 miles per second, fast enough to cross the United States coast to coast in about 6/100ths of a second. In under a single second, something the width of a planet compresses to roughly the size of a city, and the temperature climbs past 100 billion degrees. For a fraction of a second, in one place, the universe recreates conditions it has not seen since its own first moments. Then the collapse rebounds, and the star tears itself apart, and for weeks that single point outshines the entire galaxy containing it. 100 billion stars, outdone by one. Now imagine watching it from a safe distance of a few hundred light years. You would see nothing coming. A star that had sat unremarkably in the sky for your whole life would, over a few days, brighten until it cast shadows at night, until you could read by it, until it was visible in full daylight. And it would stay that way for weeks. Then it fades. The debris expands outward, thinning, cooling, and within a few thousand years, the hottest event in the modern universe becomes indistinguishable from the cold, thin gas it was born into. Everything comes back to the floor eventually. Point a telescope at the Orion Nebula, and you will see one of the most photographed objects in the sky, a glowing cloud lit from within by newborn stars. Emission nebulae like it hold gas at 10,000 to 20,000 Kelvin, ionized by the ultraviolet flood pouring off young massive stars embedded inside. 10,000 Kelvin is hotter than the surface of the Sun, and the Orion Nebula holds gas at that temperature across a region more than 20 light-years wide. A volume light itself needs 2 decades to cross. But that glowing region is a small, bright wound in something far larger and far colder. The Orion molecular cloud surrounding it stretches roughly 100 light-years, holds around 200,000 times the mass of the Sun, and sits at a temperature of only 10 to 20 Kelvin, barely a few degrees above the cosmic floor, cold enough that oxygen and nitrogen would freeze solid. And here is the contradiction worth pausing on. Those two facts are not merely coexisting, they are causally linked. Stars can only form in the coldest places in a galaxy. The reason is straightforward once you see it. Gravity has to win. A cloud collapses into a star only if gravity's inward pull overcomes the outward push of thermal pressure, and thermal pressure is just heat. Warm gas resists collapse. It pushes back. It holds itself open. Cool the gas to 10 Kelvin, and that resistance almost vanishes, and gravity finally gets its way. Every furnace we have described was born in a freezer. The hottest objects in existence require the coldest conditions in existence to come into being at all. Even within one small solar system, the spread is enormous. Venus averages around 465 degrees Celsius, about 870 Fahrenheit, hot enough to melt lead, hot enough that the Soviet Venera landers survived barely an hour on the surface before dying. Out at the other end, NASA puts Neptune's mean temperature near minus 200 Celsius, minus 330 Fahrenheit. Pluto averages around minus 225 Celsius, minus 375 Fahrenheit, cold enough that nitrogen, the gas making up most of the air in your lungs, lies frozen on the ground as ice. And yet, convert Pluto's temperature to the absolute scale, and it comes out near 48 Kelvin, which means the coldest well-known world in our solar system, the byword for remoteness and cold, still sits about 45 degrees above the cosmic floor. Even Pluto is warm, which brings us finally to the exception. 5,000 light-years away in the southern constellation Centaurus sits a small, faint, hourglass-shaped cloud called the Boomerang Nebula. Through a visible light telescope it looks delicate, unremarkable, a wisp. Its temperature is approximately 1 Kelvin. Read that again against everything established so far. 1 Kelvin is colder than the cosmic microwave background, colder than the floor, colder than the relic heat that fills every cubic centimeter of the universe and holds every passive object at 2.7. The boomerang is the only natural object we have ever found that undercuts it. Astronomers Raghavendra Sahai and Lars-Åke Nyman detected this in 1995 using the 15-meter Swedish ESO submillimeter telescope in Chile. ALMA, the Great Array of Dishes on the Atacama Plateau, re-imaged it in 2013 and resolved its structure in detail. The mechanism is not exotic. You have felt it. At the nebula's heart lies a dying star, shedding its outer layers into space at roughly 160 kilometers per second, about 100 miles every second, fast enough to circle the Earth in 4 minutes. When a gas expands rapidly with nothing to confine it, it does work pushing outward, and it pays for that work with its own internal energy. The gas cools. That is exactly what happens when you press the valve on an aerosol can, and the metal goes cold in your hand, or when compressed air escaping a tire feels chilled. The boomerang is doing that on a stellar scale, continuously, for thousands of years. A natural refrigerator running on the death of a star, with no power supply and no moving parts. And the conformation of that temperature is beautifully strange. Normally, astronomers see a gas cloud because it glows against the background, but an object colder than the background cannot glow against it. So the carbon monoxide in the boomerang does the opposite. It absorbs the cosmic microwave background passing through it, appearing as a shadow cast against the oldest light in existence, a dark patch on the afterglow of the beginning. That signature only appears if the gas is genuinely colder than the background it sits in, but the record will not last. The ALMA observations turned up something the team had not anticipated: carbon monoxide emission in regions beyond the ultra-cold zone, indicating that parts of the outflow have already begun rewarming, most likely as starlight striking dust grains liberates electrons that then deposit energy in the gas. The physics is unforgiving. Cooling by expansion works only while the expansion is rapid. As the outflow spreads and slows, the refrigerator winds down, and the background radiation, patient, uniform, inescapable, reclaims it. The coldest known place in the universe is a temporary condition. The floor always wins in the end. Now hold that against what our own species has achieved, because the comparison cuts in two directions at once. In 2021, researchers led by Ernst Russell of Leibniz University Hanover took about 100,000 rubidium atoms, cooled them into a Bose-Einstein condensate, and dropped the whole apparatus down the 120-meter drop tower in Bremen, roughly 400 feet of free fall. While manipulating the magnetic trap to slow the atoms almost to stillness, they reached 38 picokelvin, 38 trillionths of a degree above absolute zero. That is roughly 26 billion times colder than the Boomerang Nebula. The coldest thing that has ever existed anywhere, as far as anyone knows, was made by human beings in Germany. It lasted about 2 seconds. Aboard the International Space Station, NASA's Cold Atom Lab does similar work routinely, operating near 100 nanokelvin, 100 billionths of a degree, using permanent freefall instead of a falling tower. And the contrast is worth stating plainly. Nature's coldest place is sustained for millennia by nothing but a dying star breathing out. Ours lasts a couple of seconds, requires a purpose-built tower or an orbiting laboratory, and stops the instant the power does. We can beat the universe at cold. We just cannot hold it. So the inventory is complete. Stellar cores at 15 million degrees, corona near 1 billion, collapsing iron at 100 billion, nebulae glowing at 10,000 Kelvin across 20 light years. Every one of them real, measured, verified, set against a background that never moves from 2.7. And that raises the question that has been waiting quietly underneath this entire story, the one that turns a list of temperatures into something much harder to look away from. Not how hot these places get, how much room they actually take up. Everything up to this point has been about intensity. How hot, how cold, how far above or below the floor. Now the question changes, and this is the part that reframes everything that came before it. Not how hot, but how much, because a temperature tells you nothing about how common that temperature is. A candle flame and a star are both thousands of degrees. What matters, what has always mattered, is how much of the universe actually sits at each reading. And once you start measuring warmth by volume instead of by intensity, the picture that emerges is not a universe with hot places and cold places. It is a universe that is cold, with a scattering of defects in it. Start where we live and go to the nearest neighbouring furnace. Proxima Centauri sits 4.25 light-years away. In kilometres, roughly 40 trillion, about 25 trillion miles, and that number is useless. Nobody has ever felt 40 trillion of anything, so shrink it. Take the Sun, 1.4 million kilometres across, and reduce it to a ping-pong ball sitting on a table in front of you. 4 centimetres. At that scale, Earth becomes a grain of sand about 4 meters away, roughly across the room. The entire orbit of Neptune, the outer boundary of the planetary system, becomes a circle 1/4 of a kilometer wide. Now, keeping that exact proportion, where does the next ping-pong ball sit? New York to Chicago, 1,150 kilometers, 711 miles. One ball on your table, the next one over the horizon, past several state lines, and in between, 1,000 kilometers of absolutely nothing. No sand grains, no dust, nothing you could see or touch or measure with your hand. Counted honestly, roughly 30 million sun-widths of empty space lie between our star and the next. And here is why that emptiness matters thermally. Radiation obeys the inverse square law, which sounds technical and is not. Double your distance from a light source, and its intensity does not halve, it drops to a quarter. Triple the distance, and it falls to a ninth. You have felt this at a campfire. Take 3 steps back, and the warmth does not fade gently. It collapses. Now apply that from the surface of a star out to 4 light years. Alpha Centauri A is a star very much like the Sun, a genuine furnace, 15 million degrees at its core, pouring out energy every second without pause. And at 4 light years, its contribution to the temperature of anything is undetectable by any practical instrument. Not faint, not weak. Gone. Sunlight is the most powerful force acting on this planet. Move it 4 light years away, and it becomes a point of light you can barely see with your naked eye. Now widen the frame to the galaxy. The Milky Way holds somewhere between 200 and 400 billion stars, spread across a disk roughly 100,000 light-years wide. That sounds crowded. It sounds like a city. Do the arithmetic, and it stops sounding like a city. Divide the volume of the disk among the stars inside it, and each one commands, on average, tens of cubic light-years of empty space. Picture a stadium at night, with a few fireflies drifting inside it. Now consider what you would actually describe if someone asked you what was in that stadium. You would not describe the fireflies. You would describe the dark. The Milky Way is not a collection of stars with gaps between them. The Milky Way is a volume of cold, dark vacuum with a very small number of hot points scattered through it. Even where warmth exists, the region where it is useful is thinner than most people assume. Around the Sun, the conservative habitable zone, the band where liquid water could persist on the surface of a rocky world, runs from about 0.95 astronomical units out to about 1.67. An astronomical unit is simply the Earth-Sun distance, so that band starts just inside our orbit and ends a little past Mars. But those numbers deserve a warning label, and honest scientists give them one. The boundaries are model-dependent. The classic figures come from one-dimensional, cloud-free climate models, and clouds change everything. High clouds trap heat and push the outer edge further out, while thick, low clouds reflect sunlight and let a planet survive closer in. Planetary mass matters too. The same calculation shifts one way for a Mars-sized world and the other way for a super-Earth. Some published estimates place the inner edge as close as 0.38 astronomical units for a highly reflective desert planet. The habitable zone is not a line drawn on a map. It is a contested estimate that moves whenever the models improve. What is not contested is how thin Earth's own margin appears to be. Move this planet a few percent closer to the Sun, and the models suggest a runaway greenhouse. Oceans evaporating into the atmosphere and escaping to space. Move it outward, and without a strong enough carbon dioxide blanket, the water freezes and stays frozen. We are not comfortably positioned. We are threading a needle. Now pull back until galaxies themselves become points of light. At the largest scales, matter is not spread evenly. Galaxies gather into long threads called filaments, and into flat sheets called walls, and where filaments cross they form dense clusters. Astronomers call the whole arrangement the cosmic web, and every image of it looks the same, bright strands enclosing enormous dark chambers. Those chambers have a name: voids. A typical void spans something like 100 to 300 million light-years. The largest exceed 1 billion. Take the one in the constellation Boötes, identified in 1981 by Robert Kirshner and colleagues during a survey mapping galaxy distances, roughly 330 million light-years across. Based on the average density of the universe, a region that size should contain around 2,000 galaxies. Surveys have found about 60. Set that against home. Our local group, the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller companions, packs more than 50 galaxies into a region only about 10 million light-years wide. 50 galaxies in 10 million light-years here. 60 galaxies in 330 million light-years there. The same universe, arranged utterly differently. Now, the figure that reorganizes everything. Inside these voids, matter density falls to roughly 10 to 20% of the cosmic average. They are not empty. Dark matter is there, thin gas is there, a few lonely galaxies are there. But by the standards of the cosmic web, they are close to nothing, and current estimates place voids at roughly 80% of the observable universe's volume, holding something like 10% of its mass. Read that as a probability rather than a statistic. Close your eyes, pick a random point anywhere in the observable universe, and travel there instantly. You are almost certainly inside a void. 4 times out of 5, not near a star, not near a galaxy, not inside a filament, inside one of the great dark chambers with the nearest galaxy tens of millions of light-years away, in a place where the entire cosmic web is reduced to faint smudges on a black sky. That is not the exception. That is the default condition of existence. And this has a consequence that goes beyond thermodynamics into something closer to philosophy. The astronomer Greg Aldring made the observation directly. If the Milky Way sat at the center of the Botez void, our discovery of other galaxies would have come far later than it did. Follow that thought. In 1924, Edwin Hubble measured the distance to Andromeda and proved it lay far outside the Milky Way, that our galaxy was one among many. That measurement was possible because Andromeda is close, bright, and visible to the naked eye on a dark night. Now, imagine a civilization exactly as curious and capable as ours, arising on a planet near the center of a great void. They build telescopes, they map their own galaxy beautifully, and when they look outward, they find almost nothing. No bright neighbor, no local group, just an unbroken dark that their instruments cannot penetrate. Their cosmology would be complete, internally consistent, mathematically rigorous, and wrong. They would conclude their galaxy was the universe. They would not be stupid, they would simply be standing in the wrong place, which raises an uncomfortable question about our own position. Since 2013, when Ryan Keenan, Amy Barger, and Lennox Cowie measured galaxy counts in the near-infrared, a number of studies have suggested that our own region of the universe may sit inside a large local underdensity, the KBC void, sometimes called the local hole. Some analyses put it at around 46% below the cosmic average density, out to roughly 300 megaparsecs, about 1 billion light-years. If that void is real and that deep, the consequences reach directly into the argument we have already met. Matter flowing outward from an underdense region would inflate locally measured expansion rates, making the universe look like it is expanding faster here than it truly is on average, and potentially explaining part of the disagreement between the two ways of measuring cosmic expansion. But its existence remains genuinely disputed. Some studies find no evidence for an underdensity on that scale, arguing that observations extending beyond the claimed radius contradict it. Others have found deficiencies in those rebuttals. Recent work fitting velocity fields to direct distance measurements suggests any real void must be far smaller than the version needed to resolve the expansion problem. No resolution exists yet, but the possibility that our entire cosmological picture is quietly skewed by where we happen to be standing has not been eliminated. Bring all of this down to a single calculation. The observable universe has a radius of about 46.5 billion light-years. Inside that sphere sit galaxies, gas, dust, dark matter, and something in the range of 100 billion trillion stars. Now compare two volumes, not masses, not temperatures, volumes. Add up the interiors of every star that exists, every furnace, every core, every hot dense place. and compare that total against the volume of the observable universe. The stars lose by roughly 30 orders of magnitude, a 1 followed by 30 zeros. Here is what that ratio feels like. Take a single grain of sand and set it beside the planet Earth. The grain is to the Earth roughly what all the stellar matter in existence is to the space it occupies. Warm matter is not rare in the way that gold is rare. Warm matter is rare in a way that has no everyday parallel. As a share of volume, it rounds to 0. But here is where most people go wrong, and it is worth being precise, because the correction is genuinely surprising. Temperature and heat are not the same thing. Temperature is intensive. It describes how energetic the particles are, on average, regardless of how many there are. Thermal energy is extensive. It depends on how many particles you actually have. You already know this without knowing you know it. A single spark from a bonfire can be at 800 degrees and land on your hand harmlessly, while a bath at 40 degrees can scald you. The spark is hotter. The bath contains more heat. Now apply that to the largest structures in the universe. Threading the cosmic web is something called the warm-hot intergalactic medium. Diffuse plasma at temperatures between 100,000 and 10 million Kelvin, hotter than the core of the sun in places, and if you could stand inside it, you would feel absolutely nothing, because the density is somewhere around 10 particles per cubic meter. A cubic meter of the air in the room you are in contains about 25 billion molecules. The plasma has 10. Run the energy densities, and the gap is staggering. A cubic meter of ordinary room temperature air holds something like 1 billion trillion times more thermal energy than a cubic meter of that million-degree plasma. Immersed in it, your body would keep radiating heat away, exactly as though it were in hard vacuum, because thermally speaking, it is hard vacuum. The plasma is far too thin to warm anything at all. Millions of degrees. Utterly, functionally cold. That thin plasma has its own story, and it was an embarrassment for decades. Cosmologists knew from the primordial sky maps and from Big Bang element abundances exactly how much ordinary matter the universe should contain. Then they counted the stars, the galaxies, the visible gas, and roughly half of it was missing. Not theoretically missing. Missing from the ledger. Cosmologists called it the missing baryon problem, and it went unresolved for over 20 years. The suspicion was always that it lay in the intergalactic medium, but that gas is too cold to emit X-rays brightly, and too hot to absorb light efficiently, nearly invisible by every available method. Then came fast radio bursts, millisecond flashes of radio energy from distant galaxies. Different wavelengths within a burst travel at slightly different speeds through ionized gas, so the delay between them measures how much matter the signal crossed on its way here, backlighting the fog and weighing it. In June 2025, a team led by Liam Connor at the Harvard-Smithsonian Center for Astrophysics and Caltech published the result in Nature Astronomy. Roughly 76% of the universe's ordinary matter sits in the intergalactic medium, about 15% in the halos around galaxies, and just 9% makes up every star and planet in existence. The matter was never lost. It was spread so thin across so much emptiness that we could not see it. Precisely how much of that sits in the warm-hot phase specifically remains uncertain. Published estimates still span a wide range depending on the technique, from under a third to around 60%. That part is not settled. Which brings us to the honest summary of the proportion. Coal did not win this universe by force. It never overpowered anything. Every furnace we have described is still burning exactly as hot as it ever was. The stellar cores, the coronae, the collapsing iron, the nebulae glowing at 10,000 Kelvin. Cold won by ubiquity, by occupying 80% of the volume in voids alone, by filling the space between stars with 30 million sun-widths of nothing, by reducing all the stellar matter in existence to a grain of sand beside a planet, by taking the hottest diffuse gas in the cosmic web and thinning it until it cannot warm anything at all. Every warm place is a local defect in a cold universe, not a feature of it. a flaw in it, small, bright, isolated, and outnumbered by a factor no human intuition can hold. And that is the spatial picture, complete. But space is only one of the two dimensions this story lives in. Warmth is vanishingly rare in volume. We have measured that now. The harder question is how rare it is in time. To answer that, we have to do something we have not done yet. Stop looking outward and inspect a single warm place in forensic detail, because we have exactly one confirmed example, one planet where warmth has persisted long enough for chemistry to become biology. And if we take that example apart and ask what it actually required, the answer is not a short list. Start with the Sun and note that its properties are not incidental. Make it 10% more massive and it burns hotter, bluer, and considerably faster. A star's lifespan drops sharply with added mass, because the extra weight raises the core pressure and accelerates fusion. A more massive Sun might not have held a stable output long enough for complex life to appear at all. Go the other way and make it 20% lighter, and the problem inverts. A cooler star shifts more of its output into the infrared, and the balance of light striking a planet changes the chemistry of its atmosphere. How ozone forms, how greenhouse gases behave, how much energy reaches the surface in usable form. The Sun sits in a band that is neither remarkable nor arbitrary. It simply happens to work. Then the position. We have already seen how narrow the band is where liquid water survives on rock, and how much that band shifts depending on which model you trust. But notice something about Earth's place inside it. Nudge this planet a few percent closer, and models point toward a runaway greenhouse. Oceans evaporating, water vapor amplifying the warming, the whole system escaping upward until the seas are gone. Nudge it outward without a sufficient carbon dioxide blanket, and the water freezes, the surface brightens with ice, and more sunlight is reflected away, which cools it further, which grows more ice. Both edges are self-reinforcing. Cross either one, and the planet does not drift back. Now the atmosphere, and this is the number that should genuinely surprise people. Calculate Earth's temperature from sunlight alone, with no greenhouse gases in the air, and the answer NASA gives is minus 18 degrees Celsius, 0 Fahrenheit, every ocean frozen solid, top to bottom, permanently. The actual global average is about 15 degrees Celsius, 59 Fahrenheit. Water vapor and carbon dioxide, present in genuinely small quantities, supply the entire 33-degree difference between a frozen rock and a living world. Think about what that means physically. The gap between this planet and a permanent ice ball is not the Sun. The Sun would still be there. The gap is a thin film of gas, absorbing infrared radiation on its way out and sending some of it back down. Remove that film and Earth becomes exactly what everything else out there already is. Holding that film requires mass, too light, and the planet's gravity cannot retain an atmosphere against the constant leakage to space. Too heavy and it does the opposite. It holds onto hydrogen and helium during formation and grows a crushing envelope, becoming a small Neptune rather than a rocky world. And even the right mass is not enough on its own, because gravity is not the only thing stripping air away. The Sun blows a continuous stream of charged particles outward, the solar wind, and where it meets an unprotected atmosphere, it erodes it, particle by particle, over hundreds of millions of years. Earth deflects that stream with a magnetic field, generated by convection currents in a hot, liquid iron core. Mars appears to have lost that protection. Its core cooled, its magnetic field faded, and the evidence gathered by NASA's MAVEN mission indicates the solar wind has been stripping the Martian atmosphere ever since, leaving a world with less than 1% of Earth's surface pressure and water that can no longer stay liquid. Same neighborhood, same star, a dead dynamo, and a dead planet. Now the piece that almost nobody thinks about, and which may matter more than any of the others. Earth has a thermostat, and it runs on geology. Volcanoes release carbon dioxide into the atmosphere, warming the planet. Rain absorbs that carbon dioxide, and weathers exposed silicate rock, locking the carbon into minerals that wash into the ocean and eventually subduct back into the mantle. The crucial detail is the feedback. Warmer temperatures mean more rainfall and faster weathering, which pulls carbon dioxide out faster, which cools things down. Cooler temperatures slow the weathering and let volcanic carbon dioxide accumulate again. The carbonate-silicate cycle, a negative feedback loop operating on timescales of hundreds of thousands of years that has kept this planet's temperature inside the liquid water range across billions of years, while the sun itself has steadily brightened. And it requires plate tectonics to work, moving crust, subduction zones, active volcanism. A planet with a stagnant lid has no such regulator. The chain keeps going. Earth needed its water, delivered during the chaotic early solar system by impacts from bodies formed further out, enough to fill oceans, not so much as to drown every continent. It needed a large moon. Without one, models suggest Earth's axial tilt would wander chaotically over millions of years, swinging the poles toward the sun and back, driving climate shifts far more violent than anything in the geological record. And then the item that is genuinely disputed. For decades, Jupiter was described as Earth's shield, a gravitational bodyguard, flinging dangerous comets out of the inner solar system. But simulations by researchers including Jonathan Horner and Barry Jones complicated that picture considerably. Jupiter deflects some impactors away, yes. It also perturbs others inward, and it stirs the asteroid belt in ways that send material toward us. Whether the giant planet is a net protector, a net hazard, or roughly neutral remains an open question, and the answer appears to depend heavily on Jupiter's exact mass and orbit. The shield may be real. It may also be partly a myth we told ourselves, and every item above assumes the raw materials already existed. The iron in Earth's core, the silicon in its rock, the oxygen in its air and its oceans, the carbon in every cell of your body. None of that existed in the early universe. The first 20 minutes produced hydrogen and helium, and almost nothing else. Everything heavier was manufactured inside stars and scattered by their deaths, which means this planet required prior generations of stars to live and die first. It required a molecular cloud, cold and dense enough for gravity to win. It very likely required a nearby supernova to seed that cloud with heavy elements and possibly to trigger its collapse. The chain of conditions does not begin with Earth. It reaches back through the entire history of the galaxy, which raises the question everyone wants answered and which we cannot yet answer. Two positions have been argued for decades. The rare Earth view holds that the full chain, right star, right orbit, right mass, magnetic field, tectonics, water, moon, is so improbable in combination that complex life may be extraordinarily scarce. The Copernican view holds the opposite, that we have simply mistaken ordinary conditions for special ones, as people have done repeatedly throughout the history of astronomy. Both positions are argued by serious scientists. Neither can be settled because we are working from a sample size of 1, and a sample of 1 has no statistics. Kepler gave us the first real data. An analysis led by Eric Pettigura in 2013 concluded that roughly 20% of Sun-like stars host an Earth-sized planet in the habitable zone, the famous 1 in 5. But that figure is far shakier than the headline suggested. Published estimates of the same quantity have ranged from about 1% to over 30%, depending on the assumptions. A later analysis led by Steve Bryson at NASA Ames, using the final Kepler catalogue and improved stellar data from Gaia, put it nearer 50% under a conservative definition and 75% under an optimistic one. And a 2023 reassessment noted that after Gaia corrected the stellar properties, the reliable Earth-sized candidates in the conservative habitable zone dropped to essentially 0. The number is not converging. It is a moving target with error bars nobody likes. Even the total count is contested. A widely quoted 2016 study, extrapolating from Hubble's deepest images, concluded the observable universe contains at least 2 trillion galaxies. That figure went everywhere. Then in 2021, a team including Todd Lauer and Mark Postman used NASA's New Horizons spacecraft. 4 billion miles out, 6.5 billion kilometers, far beyond the dust that brightens the sky near Earth, to measure the faint combined glow of every galaxy in existence. From out there, the sky is about 10 times darker than the darkest view Hubble can manage, and the glow was too faint. In Postman's words, we simply do not see the light from 2 trillion galaxies. Their measurement points toward hundreds of billions instead. Other researchers dispute that reading, arguing the observation constrains total galactic light rather than galaxy count. The argument continues, but the confident trillion-scale figure has been pulled downward, and honest accounts should say so. Here is the part the occurrence rate debate tends to obscure. Orbital position is only the first filter. A planet in the habitable zone still has to hold an atmosphere, generate a magnetic field, run a functioning geological thermostat, acquire water, and avoid tidal locking or chaotic obliquity. Each condition removes candidates from the pool, and they multiply rather than add. For the first time, we can actually test some of these. JWST is now performing transmission spectroscopy on rocky worlds, watching starlight filter through a planet's atmosphere during transit, and reading which molecules absorbed which wavelengths. That instrument is testing directly whether small planets around small stars retain atmospheres at all. The early results have been sobering for several targets, but the work has barely started, and whichever way the occurrence rate lands, the volume arithmetic does not move. Even under generous assumptions, the total volume of space where warmth and liquid water coexist, compared against the roughly 10 to the 80th cubic meters of the observable universe, still rounds to zero. So warmth is vanishingly rare in space. That much is measured. The harder question is whether it is any less rare in time, and the answer runs through the most reliable law in physics. The second law of thermodynamics says that isolated systems move toward equilibrium. Heat flows from hot to cold, never spontaneously the other way, and differences even out until nothing is left to drive anything. A cup of tea cools to room temperature. It has never once, anywhere, warmed itself back up by drawing heat from the room. Apply that to everything, and the universe has a direction, toward uniformity, toward cold. Stars look like a rebellion against this. They are not. A star resists locally, holding itself hot by fusion, radiating light outward for billions of years. But every photon it releases travels into expanding space, stretching and thinning and never returning. Locally, a star is an island of order. Globally, a star is an accelerant. It takes concentrated energy and spreads it thinner, faster than anything else in nature. Stars are not fighting the cold. They are how the universe spends itself, and the spending has already passed its maximum. Star formation across the universe peaked roughly 10 billion years ago, a period astronomers call cosmic noon. Since then, the rate has declined steadily. The gas available for making new stars is being locked into remnants faster than it is being returned. Our galaxy is not filling up. It is running down. We arrived late. The current era, the one where matter is arranged into stars and galaxies, and most energy comes from fusion, has a name and an expiry date. Fred Adams and Gregory Laughlin called it the stelliferous era, and current estimates run it out to around 10 to the 14th years. 100 trillion. The last lights will be the red dwarfs, burning so slowly and mixing their fuel so thoroughly that some may last 10 to 15 trillion years. Then the sky goes out. What follows is called the degenerate era, a universe of remnants. White dwarfs, neutron stars, brown dwarfs, dense corpses, still faintly warm, radiating away what heat they have into a background that keeps dropping, cooling, always, toward the floor. How that era ends depends on physics we have not confirmed. The standard account has protons slowly decaying, dissolving ordinary matter from the inside out over something like 10 to the 34th years or longer. But nobody has ever observed a proton decay. Enormous detectors have watched enormous volumes of water for decades and seen nothing. the prediction remains unverified. If protons do not decay, other models take over, including the extraordinary possibility that white dwarfs, over timescales so long the numbers stop meaning anything, slowly fuse their interiors into iron and detonate as black dwarf supernovae, the last explosions in the history of the universe, separated by unimaginable spans of silence. After that, black holes inherit everything. They are not permanent either. Stephen Hawking showed they leak, radiating away with agonizing slowness, and the smaller they are, the faster they go. Stellar mass black holes are estimated to evaporate somewhere near 10 to the 67th years. The supermassive ones at galactic centers may last until around 10 to the 100th. Even that endpoint is unsettled. The black hole information paradox, the question of what happens to information that falls in and whether it comes back out in the radiation, remains one of the deepest unresolved problems in theoretical physics. Nobody can yet say with confidence what the final state of an evaporating black hole is. Now compress the whole thing, take the entire future, from now until the last supermassive black hole finishes evaporating, and map it onto a single calendar year. Every star that will ever shine in every galaxy has already gone dark before the first second of January. The first is over. Not the first day, not the first minute. Inside a sliver of the first second so small that no human unit of time can represent it honestly. That is the age of light. The entire lit chapter of cosmic history, every sunrise, every photosynthesizing leaf, every eye that ever opened, occupies a flash at the very start of a year that is otherwise dark and cold from end to end. And in a genuine twist, the ending itself has become contested, recently, and by observation rather than theory. If dark energy is a true constant, the universe expands forever and cools forever, and the picture above holds. But results from the dark energy spectroscopic instrument, combining the largest three-dimensional map of the universe ever made with supernova and background data, hint that dark energy may be weakening over time. The preference for evolving dark energy over a constant sits somewhere between about 2.8 and 4.2 sigma, depending on which supernova dataset is used, short of the 5 sigma threshold physics demands, and disputed. Several researchers, including George F. Stathiou, have argued the signal depends heavily on dataset choice and may reflect calibration problems rather than new physics. But the stakes are the whole ending. Constant dark energy gives eternal expansion and heat death. Weakening dark energy makes a recollapse, a big crunch, conceivable again, and a stronger phantom form would tear structure apart in a big rip. The thermal fate of the universe is not settled fact. It is an open observational question, and the data are still coming in. Long before any of that, this planet has its own schedule. The sun brightens as it ages, and in roughly 1 billion years, current models suggest its rising output will push Earth past the point where oceans can persist, evaporating the seas and ending the surface water that made all of this possible. Roughly 5 billion years from now, hydrogen exhaustion in the core will swell the sun into a red giant, expanding past the orbit of Venus. The same warmth that assembled biology becomes the heat that ends it, not through malice, not through catastrophe, simply because a star cannot burn steadily forever, and the thing that gave us the exception is itself part of the process running down. So let us come back to the original question and answer it properly. Space is not cold in the way you have felt cold. No wind out there, no bite, nothing pressing against skin. Space cannot chill you, because chilling requires contact, and space has almost nothing to make contact with. Space is empty. Space is indifferent, and it takes your heat only because nothing sends any back. The number was never the terrifying part. 2.72548 Kelvin is just a reading. What should stay with you is the proportion. 80% of the volume in voids, 30 million sun-widths between one star and the next, all the stellar matter in existence reduced to a grain of sand beside a planet, and the entire age of starlight compressed into an unmeasurable fraction of the first second of a very long year. Warmth is not the rule, with cold as the exception. Warmth is the exception. Local, temporary, and outnumbered in space and in time by margins the mind refuses to hold. Think back to that candle in the cold, unheated room, the one whose warmth was not arriving from anywhere, only leaking outward into everything around it. The room has no walls, the room is everything, and the candle is not something you are watching from across the floor. You are standing inside the flame. Everything that has ever lived, every conversation, every discovery, every ordinary afternoon happened inside that small, bright exception, in the brief interval before the heat finished leaving. None of this asks for fear. Fear would be the wrong response entirely, and it would waste the thing itself. What it asks for is attention, warmth on your skin, light on a wall, a planet that is, for now, the exact temperature at which water stays liquid and a body stays alive. The exception is holding. That is enough. Right now, without trying, you are giving off about 100 watts of heat. You have done it every second of your life. You will do it tonight while you sleep. In almost every place that exists, that warmth would simply leave, out into the dark, thinning, reddening, never returning. That is the default. That is what the whole universe is doing. But not here. In this room, on this planet, the heat you give away comes back from the walls, from the air, from the person asleep in the next room, giving off their 100 watts, some of which reaches you. Every hand you have ever held was warming you with energy. It could not keep either. That is the exception. Not just that warmth exists, but that here it is exchanged instead of lost. You are not a small thing in a cold universe. You are one half of the only conversation the universe has ever managed to have with itself in heat. Thank you for staying with me this long. If tonight meant something, a like and a subscribe are how you tell me. More journeys are coming, quieter ones, stranger ones. Sleep well. Somewhere nearby, someone is keeping you warm without knowing it.